we're going to work on graphing inverse functions. We're actually going to work on finding the equation for the inverse function. And in trig, the inverse function is called the arctan, or the arc sine, or the arc cosine. And we'll get to that in a minute, okay? A couple reminders just in general about inverse functions. To find the inverse of an ordered pairs, we just switch the coordinates. So if I had the ordered pairs 5, 4, that's a 4. If I had 3, 2, and negative 1, 5, then the inverse of that relation would be 4, 5, 2, 3, 5, negative 1. Okay? That's how we would find the inverse if they just give us coordinates. We just switch them. The domain and range switches. Okay? Now, if they give me an equation, let me slow this down a little bit so we stay on the same page together. If they give me an equation like y equals 2x plus 5, then what I do is I switch the x and y around. Oops, sorry. The x and y around. I guess I couldn't find it. I switch the x and y around, and then I solve for y. And so this y equals 2x plus 5 becomes x equals 2y plus 5. Subtract 5 from both sides, divide everything by 2, I get y is equal to x minus 5 over 2.
Can't you just flip all the sides? Like instead of multiplication, you know it's going to be divided, and instead of adding by, you know you're going to be minusing by.
Yeah, you have to be a little careful there. I'm not just dividing the x by 5, or by 2. I'm dividing the whole thing that's left over there by 2. And so there are some things, especially if you get into squares, there's some things you have to be careful with. It may not end up exactly where you think they're going to end up. Okay? So at least for a while, go through the process of doing it this way so that you don't make some mistakes that you don't foresee. Remember, the inverse may not be a function. I think I wrote the inverse function may not, that's why we have a strange gap there. Kind of right here. I think I had the word function there. And the whole point of this statement is to recognize that it may not be a function. So you should just write what I have here. The inverse may not be a function. Okay?
Wait, is it saying that it's impossible, or that it's possible that it's not?
It's possible that it's not. It's possible that it is.
Okay.
I'm just saying that just because I have a function when I take the inverse of it, doesn't mean I still have a function.
Yeah, because I interpreted inverse may not.
For example, something you've already covered is a parabola. We know a parabola is a function. It passes this vertical line test, doesn't it? No matter where I run this vertical line across there, it's never going to touch more than once. Do you agree? Okay. The inverse of this would reflect over the inverse of this would reflect over this y equals x line, this red dotted line I drew here. And so it would look like this.
That would not be a function.
And then, if we look at that with the vertical line test, we realize it's not a function. The vertical line crosses that graph multiple times, more than once, doesn't it? Okay? When I say multiple times, I mean it's crossing twice there, and twice there, and twice there, and twice there. And so multiple times can I find where it crosses the graph more than once. So that means that the function's inverse is not a function. Okay? So this statement here is just simply saying the inverse may be a function, may not be a function.
Yeah, I just kind of.
Maybe I could say that may or may not. May or may not be a function. Maybe that's what I had originally. Okay? You don't have to erase it. You can, I mean, you add what you think is best for you to understand what I'm trying to say there. Okay? That's a lot. So may or may not be a function. The graph of the function in the inverse is a reflection over this y equals x line, which is this one that I had drawn in right here. That line there represents y equals x. Anybody tell me why that line is called y equals x?
Because the y value is the exact same as x value.
Yeah, everywhere on that line, whatever the y value is, that's what the x value is. Whatever the x value is, that's what the y value is. So right here we're at 3, 3. Here we're at -1, -1. Right in here we're at -2.7, -2.7. No matter what it is, the x value, no matter what the x value is, the y value is the same. Okay? And so then this graph that I've drawn here is similar to the one I've already drawn up there. Just to show you that's a reflection of that line. I didn't do a great job of drawing my parabola there either. Okay? So you don't have to redraw that. Any questions on this page? All right.
Is this an example?
What's that?
Is this going to be an
I think we want to talk about the domain and range here. Okay, this slide doesn't match my notes that I was expecting. But you know, always like to make lemonade out of lemons, right? So we'll talk about the domain and range since we have to anyway. And so we're just, in the original right here, we're just pointing out that this number here is some number between -1 and 1. Because the largest possible sine value of any angle is 1. The smallest possible sine value of any angle is -1. So this number out here has to represent some number between -1 and 1. So what's my range?
Y is greater than or equal to -1 and less than or equal to 1.
Yeah. Okay. So that's my range of this one up here. Okay. Now, x is some angle. And so my domain, let me use a colon again, be consistent, is any real number. Okay. My domain is any real number, all real numbers. Maybe all real numbers make more sense for you. I'm just saying you could use any of them. They're all going to work. You can take the sine of any angle you want. You want to take the sine of 1,000,000 degrees? Then use your calculator and say, what's the sine of 1,000,000? And hopefully you understand now what that means. 1,000,000 degrees means there's 360, there's 720, there's 360 more. I'll lose track of it. And I keep doing that until I figure out where 1,000,000 is, right? And if I had lots of spare time today, I'd say, do it. Show me, what quadrant is 1,000,000 in? Is it? No, you found the sine of that angle. What quadrant is that angle in? So you got a positive number?
Can I just take 1,000,000 divided by 360?
A million divided by 360 will tell you how many times it went around.
Only the best one.
And so then if you subtract the whole number from that and times it by 360, you'll figure out how many, so you get just a decimal. Let's do it. It just takes a minute. A million divided by 360.
283.
A million
I get
divided by 360.
52,777.7.
Repeat. So subtract the 2777 from your answer. And times it by 360. So you had a negative 0.9 then, right? Oh, okay, I didn't see that. So what that's saying then is we went around 2777 times, 2,777 times. And we had to stop down here at 280 in quadrant 3. And so that's the same as
Isn't that quadrant 4?
this angle, negative 80. And it's the same as this angle, a positive 280. Okay? So that's the unit circle work that we've done. Hopefully you understand that. All right? But my point is, it doesn't matter what that angle is. There's going to be a sine of that angle. And it's going to put it right back into terms of between 0 and 360. Okay? And the negative 0.94, is that what you got? 0.98. Negative 0.98 you got? That's really saying it took, and this is important for today, and we'll talk about more later, so don't feel you have copy down yet. But the sine value, all possible sine values are found from negative 90 to a positive 90. Or negative pi over 2 to a positive pi over 2. All the negative values are here in this quadrant. All the positive values are in this quadrant. So all the possible values of sine can be found in those two quadrants. Same for tangent. Actually, sorry. It is the same for tangent, but they don't use those for tangent. Tangent uses the same one we do for cosine. And so, all the possible values of, all the possible values of sine and cosine are found in those two quadrants. I misspoke. Cosine and tangent. We just said the yellow is the sine, and this is the cosine in the tangent. Okay? All right? So, if I reverse this now, if I take, inverse, if I take the inverse of this, then what's going to happen to my domain?
It's going to change.
What's my domain of the inverse?
It would have to be in between 1 and
Negative 1 to 1. And my range?
It would be any of
Okay.
Did you just
Did I what?
flip-flop the minor?
I did flip-flop them. On purpose, though, because what did I do to get my,
them. Just switch places with them.
what did I do to find my equation?
You switch.
I switched my x's and y's, which means I switched the role of the domain and range. Okay? Right here I switched my x's and y's, and I solved, and so that in turn switched my domain and range. And so, whenever you're looking at inverse of another function, then what that means is you've traded the domain and ranges. Okay? Sometimes we run into some problems switching domain and ranges. And so we have sometimes restricted domains. And that's what this is all about right here. These are restricted domains. Okay? And we're about to talk about that right here. Just reminding you of what the sine graph looks like here. Can you see that this right here is red.
Yes.
No.
Okay, it is. My, let me make it yellow. That shows up better.
Still hard to see.
Either my projector is going a little bit bad, or I don't know how to set it. But the color just doesn't come through on the screen like it does on the computer. But anyway, those are the restricted domains. And this is what I was talking about just a minute ago. And so this one is y equals cosine of x. This one was y, up top is y equals sine x. And this little bit from 0 to pi represents the restricted domain of the cosine graph. And from negative pi over 2 to pi over 2 represents the restricted domain of the sine graph. Okay? We don't have tangent on here, but tangent would also be 0 to pi. If we looked at it, I guess I could draw something here real quick. That first tangent looks like this. So everywhere from negative pi over 2 to pi over 2. Actually, probably with tangent, it makes more sense to you why it would be negative pi over 2 to pi over 2, because that shows that whole graph. And then this graph is repeated over here, and it's repeated, to the right of that and to the left of that. It just keeps repeating this same one. Well, it's a little harder to see it, but these values, all the possible sine values between here and here, are being repeated over again. This part right here is the same as this part here was. This part down here is the same values as this down here. Their x values don't match up, but their y values do. The sine, the range values all match up. Okay? All right, then below. I'll move that back up if you didn't get it. It says no. Capital letters mean the trig functions have restricted domains. Okay? Capital letters mean the trig functions have restricted domains. So if your geometry teacher got after you to write sine, cosine, and tangent with a small letter, it's because they knew what was coming later on. Capital letter in sine, this letter right here, means that has a restricted domain. Means it's only talking about the domain values between negative pi over 2 and pi over 2. Or negative 90 and a positive 90. Okay? This capital letter means it has a restricted domain. It's only talking about the angles between 0 and 180, or 0 and pi. And same with the tangent. Okay? Does anybody not copy down this first statement here so I can slide this up just a little bit more? Okay, let me pause that so you can copy that down. What I have drawn here is a tangent function graph. The black line, or the black curve, this one right here is a tangent. And it's only between negative pi over 2 and pi over 2. Oh, I didn't realize what I had done. I misspoke earlier. I said the tangent would be between 0 and pi like the cosine. It's not. It's between negative pi over 2 and pi over 2 like the sine, which is what I then later said when I looked at the graph earlier, or just a little bit before when I went back to here. Oops. Right here I said it was negative pi over 2 to pi over 2, but when I talked about it on the slide before, I said it the other way. So tangent and sine are here, and this is the cosine's the only one that's 0 to pi, okay? All right, so if I reflect that over this red line here, y equals x, then I get this green graph, which is right here. Okay? If you're asked to draw the inverse, you might find it easier to draw the original first and then reflect that over the y equals x line. And so this wing right here, or this branch right here, okay, if I reflect that over, whenever it touches the line like here and here, then the inverse is going to touch the line there also. So if this went just below it, then the inverse is going to go just above it. And if this continued on beyond the line here, then this inverse is going to go above it and continue on over here. And I can do the same with the bottom half. So if I look at the function, it went just above it now, intersected the line at this point and this point. And so the inverse is going to go just below it, intersect at those same 2 points and continue on. Okay? That's how I graph it. I find the inverse is confusing to look at. But if I look at what the original is doing, then it's easier for me to look at the inverse. And sometimes they'll give you the inverse, they want you to go the other way, and then you still can graph it that way. And don't be afraid to use your calculator to draw your graph, make sure you know what you're looking at. The key is to understand what your domain is, yeah.
So if you want these graphs like drawn, do you want like points, like the inverse points plotted, or do you?
You do not have to make a table and find me 5 or 10 points. But it is good, especially if it's a confusing looking graph, it's not just a simple y equals tan x like this one was.
Yeah.
Then you might want to plug in a couple points to give you an idea where it's going. Okay, and once you find a couple, you know what the other half's going to do, right?
Yeah.
I mean, if I graph y equals tan 3x, if I graph y equals tan 3x, I got an idea it's going to look like this. I just don't know exactly where some things are. So I might make a table and find a couple x values between 0 and 90 to show me what's going on over here. And then they'll tell me it's doing the same thing on this half. So I don't need to do a lot to give me a lot of information on this. Okay? But yeah, that's a good question. Any others? Write the equation for the inverse of y equals arctan 1/2 x, then graph the function and its inverse. Okay? So I got this started. I said x equals arctan of 1/2 y. Notice the capital A in arctan. Talk about restricted. So what would I do to undo an arctan? I find the tangent of both sides. And because that is a capital A, I'm going to do capital tangent of x is equal to, and when I tan this, when I tan the arctan, they cancel. So I'm left with 1/2 y. Now what do I do? Multiply both sides by 2. So y is equal to 2 tan x. Some people might think that is y equals tan 2x instead of y equals tan 1/2 x. They just switch that 1/2 into 2. Megan, that's what I was talking about before. You have to be a little bit careful about what you're doing. You're right. If they're adding over here and adding and dividing, I'm going to be subtracting and multiplying. But where I do it and what I do it to might change depending on the function. Here, my 1/2 was inside the function. Now it's my 2 is outside the function. Okay? So you need to go through the process a few times to understand what's happening. And I agree that some of them will be easy, and once you figure it out, you can just skip right to it. I'm not asking you to do a bunch of tedious work that you already know. I just want to make sure you know what's really happening first. Any questions on how I rewrote my equation? Okay? Now let's graph. Okay? If I graph this one first, it's restricted domain, so I'm just talking about between pi over 2 and negative pi over 2. Alright? And so this is pi over 2. Okay? With this 2 out front, what's that really doing? Well, instead of being at 45 and 1, which is what tangent would be, right? Tangent of 45 is, for you calculator if you don't know that, or tangent of pi over 4.
1.61.
Tangent of 45,
It's 1.
you're not in the right mode.
You're in radians.
So if you're in radians, then use pi over 4. If you're in degrees, use 45. So anyway, you get 1, right? Well, this is saying I'm taking whatever that tangent is, I'm times it by 2. So instead of being at 1, I'm going to be at 2. So my graph is going to look like this. And then here and 2. It's hard to graph that with my shadow. So it looks like that. Okay? Then the inverse is going to be the reflection of that over, I'm sorry, see this was the inverse in this case. So the original is still going to be the reflection of that over this line. And so I get this. So 1. That. Okay? So that's what my two graphs will look like. And if you graph them on your calculator, you should get something similar. If you set your domain and range up properly, it'll look the same. Okay? All right. We took a lot of time to do this. Your assignment today, oh, I didn't write it down.
No assignment.
Your assignment today is, it's actually going to be 7 through 39 between today and tomorrow. 7 through 39. I wrote 7 to 19 today and 21 to 39 tomorrow. It really doesn't matter. Between the 2 days is 7 to 39. Odds always.
Yeah, it's always Meg.
I'm so sorry, Alex.